Okay, good afternoon. We'll go to plenary talk number 19 by Professor Gyula Katona, and I invite Professor Arumugam to chair this session. Professor Arumugam.
I welcome again all the participants to this plenary lecture by Professor Katona from Alfred Rennie Institute, Budapest, Hungary. He is well known as an expert in combinatorics especially, and he is a member of the editorial board of more than 20 journals across the globe. And he has organized more than 15 conferences, and his research interest includes combinatorics, extremal problems in graph theory, databases, search theory, and cryptography. He has an excellent publication record, and one of his classical papers has crossed 900 citations so far. And he has visited India so many times, and I have listened to his lectures in several places in Tamil Nadu and Delhi and other places. So now I invite him to his online talk on when the light depends on the target. So Professor Katona, please.
Thank you very much for the introduction. Actually, this would have been my 17th visit to India, but it didn't happen. So thank you for the invitation. It's a great honor to me that I can take part of the celebration of this mathematical genius of India. Of course, it would have been much better to have this celebration in person in India. Therefore, I really hate COVID-19. As a revenge, I will speak something about which is related to the fight against it. So I will start my subject with some introductory examples. So in World War II, when people were trying to find soldiers infected by syphilis, they realized that, of course, they had to take a blood test from everybody, but the chemical part of the test shouldn't be. It's not necessarily to make it for every single blood test, but you can pour together some samples and check them together if there is one. So you take a subset and you ask of the soldiers, and you ask if there is at least one of them infected. And this is why it's called by some people group testing, what I don't like, because it's nothing to do with the mathematical concept of groups. Today, the test is different, not blood, but saliva. The second example, when Rennie's car broke down in the 60s, and people repairing Western cars were not very advanced. So he had to find the problem himself. And so he applied this theory again, that doing some tests, start the engine or some others, it showed that the broken part is in the subset or not. And the third example is a chemical analysis. So you have a solution which contains one unknown metal. And so the set is the set of metals, and this is the set of alkali metals. And so when you adding a drop of certain chemical, the solution changes color only if the metal is an alkali metal. So after this, you can easily understand the basic model of the search is that we have one unknown element in a finite set X, and you want to find this. In the case of blood test or test of infected people, it's not true. You have more, but this for most of my talk, I will speak about a case where we know that there is exactly one unknown element. And the questions of type, if X is in A, can be asked. So this is a subset A, where A can be chosen from a family of script A. So you cannot choose every possible A. Like in the case of car, it's obvious that you cannot take arbitrarily a subset of the parts because you cannot test them together. So the mathematical problem is that find the smallest number of questions determining the unknown X uniquely. And there are two basic directions, the so-called adaptive search, when the choice of the next question may depend on the answers of the previous questions. So you can ask A first, and when the answer is negative, that is not in this set, then you ask this question. If the answer is yes, it is in, then you ask this question. The questions can be ordered in a tree structure. So you start with a set A, and if the answer is 0, then you ask A is 0. If answer is 1, then you ask A1, and so on and so on. And the unknown element is uniquely determined at the end and at the leaves. And then the length of the search is the depth of the tree. So we consider the worst case. That's the length. So for the given algorithm. And of course, the mathematical problem is now to minimize the length of the search. So the all possible trees, and you want to minimize the length, so the depth of the trees, and this will be denoted by lowercase a, script A. This stands for adaptive for the given family, and the non-adaptive search is in contrast. We choose the questions in advance, A1, A2, AM from the given family, and no matter what answers are obtained, we just continue, we ask all of them. So you can ask them immediately, all of them. And so what they must satisfy, that for any two elements, distinct elements, X and Y, there must be a set in the family such that either X is in A and Y is not, or the other way around. So there is a set which separates X and Y. And this is called the separating family. And now the problem is, what is the minimum size of the family, subfamily? So number of sets, such a way that they form a separating family. And so there are some trivial statements that it should be at least log n, because even in the adaptive case, because the number of possible results can be halved at each step. So if you take a subset, either the subset or the complement has size at least half of the previous one. So you always half of the possibilities. So you know you need this is of course a log of base 2. So you need this much, and this inequality is obvious that you are faster if you are adaptive than in non-adaptive. On the other hand, there is an separating family of this size. The next picture shows it. So the first question, it takes half of the underlying set. The next question, the green question, takes half both of them. So it's kind of perpendicular to the first question. And then the third question, third subset, takes half all of them, and it's obvious that this needs only log, of course, ceiling of log n. I'm sorry, I go back. So this is why we can finish it with log n. So this implies that in this case, when all a's are allowed, then this is exactly the length of the algorithm in both cases. It doesn't depend. Now, Rainey asked this question: if you take, I hope this notation is clear, the family consists of all subsets of size at most k. And we suppose that k is at most 1/2, because otherwise the complement is smaller, so there is no restriction. If k is more than n/2, then it's not a restriction. And so here I consider first the adaptive case, when we can use sets of size at most k. And that's a very easy looking algorithm. You take a k element subset, and if the answer is yes, then you find the unknown element in this part, taking the halves all the time. If the answer is no, negative, then you take another k element subset, and so on. You go on. When you find a positive answer, then you find the element halving the set, unless you arrive to this situation when the remaining part has at most 2k, and then you can find the unknown element in this part by halving. Earlier you cannot do, because you have more than 2k, and you can use only sets of size at most k. And this is, I'm sorry, I didn't finish this page. And so this is the optimal algorithm. One can prove this is almost trivial. It's interesting that it's much more difficult mathematically to find the non-adaptive optimum. And I don't want to waste time, but it has been determined when k is proportional to n, then this is the asymptotical result, but it's algorithmically it is determined, this value exactly. So, but it's an old result, but at the very end, you will see a generalization of this. So it may take some, it has some importance for my talk today. So this is actually I repeat, the minimum number of subsets of size at most k, such a way that they are separating the underlying set of n elements. a big problem arises when there might be lies. So when the answer to this question can be incorrect. Of course, you can consider that every answer can be incorrect with probability P independently, but this leads to a different theories. It's not combinatorial, it's more probabilistic. It is easier to treat the problem when you suppose that at most E of the answers can be incorrect. It's of course, it's closely related. In coding theory, you also suppose this condition instead of the probabilistic condition. And this is called the Rényi-Ulam game. I don't want to tell the history. And actually, the non-adaptive case is equivalent to the basic question of coding theory, when we can use every subset. And the difference here between coding theory and combinatorial search theory is that the conditions which are natural are very different in coding theory and in combinatorial search. And the adaptive case is so-called coding theory with feedback, and Berlekamp made a very nice deep theory of this, and there is a quite recent survey by Deppe. But in this traditional model, the lie does not depend on X and A. So it happens after it. So it's now I will show some examples when the answer might depend on the question and the target, what we want to determine. So in the case of chemical analysis, when you drop a certain chemical to the solution, then it can happen that there are some unknown parameters like the temperature, which for certain metals might change the results. So there is a lie here in the answer. And but for certain metals, which you know that the answer is sure, for certain, you don't know that it is sure. So it depends on an X, if there is a lie or not. The other examples is criminal investigation. So suppose that someone was killed. So these red dots are blood. To make it clear, Hun in Hindi. So there is a set of suspects. X is the set of suspects. And one of the tests is asking a question from a witness. Was the murderer taller than 190 centimeters? And here the set of suspects taller than 190 is a subset of X, of course. We can suppose that the witness will tell the truth unless the murderer is a close relative or friend of him. So again, the lie, the existence of the appearance of a lie depends on X. So this is the new model. Not so new, you will see it, there are some paper published. So the new model relative to the Rényi-Ulam game is we have a partition instead of just a set and the complement. We have a partition ABL, this stands for lie. So this is the positive part and the negative. So when X is in A, the answer is yes, and we know that the answer is correct. If X is in B and the answer is no, we know that the answer is correct. But if X is in L, the answer may be yes or no, and we don't know anything about its validity. So in other words, if the answer is yes, then we know that X is in this set, A or L. If the answer is no, then we know that X is in this one. So L is always added to the answer. I mean, size to the set of possible solutions. So now the mathematical question is again that under these conditions, what is the minimum number of tests? Of course, if this is allowed, so we allow the empty L, then there is it's not a new problem because we can suppose this one and we can use the old situation. So we have to suppose something, for instance, that L, the size of the bed elements has at least K, so where K is a fixed integer. And a theorem of Tickler and myself says that the best adaptive algorithm is the following, that the time is running, so I have to skip basically this. That the first question is, of course, this, that K and these are equal, and we always put so suppose that Z is the set where we know that the unknown element is located. So it must be here and it is not here. And we want to reduce Z. And when this part is smaller than K, then we choose the L to cover all these and take half of the rest, and so on. I don't don't show the rest of the algorithm because it's so obvious, and this is the result, which looks terrible complicated, but this is negligible. So it is basically n over n minus k over 2. So I am speaking today more on the non-adaptive search. So in this case, we have a set of triples where the middle ones have size at least k, and for every pair there is an I such that either, so for every pair x and y, there is either there is a triple in such a way that either x is in A and B is in Y, or the other way around. So we say strongly separating, because this L cannot separate anything for any other element. And so the question is, of course, minimize M, which is strongly separating, under this condition that the middle part has size at least k. And so the question is the minimum of M. And there is a very surprising result that it's easy to prove that this inequality holds for K and M. And the second inequality is that this inequality holds for N, K, and M. And the non-trivial part is that these are the only conditions. So the minimum M for the problem is the smallest M which satisfies both inequalities here. And the proof is based on a result about the n cube. And n cube is Vn is a graph with vertex at 0, 1 sequences and two vertices adjacent connected by an edge, if and only if the sequences differ in exactly one position. So the Hamming distance is 1. And of course, a matching has different endpoints. And the direction of an edge is the position where the two vertices differ. And so this is a matching. And in the 3 cube, so the red ones form a matching. And what we want here, what we need in this statement is that the directions are distributed among the possible directions equally. So in this case, in each direction, there is one edge. So the number of vertices of Bn is 2 to the n, and the number of edges in a matching is at most 2 to the n over 2, so 2 to the n minus 1. So in one direction, you cannot have more than this number. And so this is our theorem, which is needed to the previous, to the proof of the previous theorem, that Bn contains a matching like this. In the case of C, this is trivial, but for N, it is a non-trivial construction. So the organizers successfully moved the conference to the virtual reality, but there is one thing which they were not able to do. I am missing very much the fantastic evening of Indian dances and music. And yeah, next time. This time it probably looks like this. Okay, so now this almost end of my time, I start to speak about the new results. So the stronger assumption is, instead of supposing, before we suppose that this has a size at least k, and instead now we suppose that this has size at most a and this has size at most b. And of course, L must be this one. So this is a stronger assumption. And the special case when B is equal to n minus a gives that this has size a and this has size n minus a. And of course, L has size 0. And this case was settled at the beginning. I mentioned in a paper of 1966. The adaptive case is easy, similar to the previous one. So the mathematically interesting problem is this now, that you have to find the minimum number of such triples such that I didn't repeat the condition that the size, this is at most A and this is at most B. Oh no, so this is the, I made an error here, I'm sorry. So I didn't change this condition to the real one. So this was the old condition. So instead of this, we should have the condition that this has size at most A, at most B, at most A, at most B. And it is a strongly separating family. And Now I show you an equivalent formulation. So this is the condition that for every pair you need a set of size at most A and another set at most B, of course, the joint ones. And this can be formulated in this way, that for every pair there is an edge connecting this. So this pair can be described as a complete bipartite graph. So the question can be asked that determine the minimum number of complete bipartite graphs with this condition that the sizes have size at most k, at most b, and they are covering the complete graph kn. So after all of these applications and motivations, we really considering a problem of covering the complete graph by bipartite graphs. So in this case, when we have n 4 vertices and the sizes are 2 and 1, then this is a covering. Actually, this disjoint covering, so it's a decomposition. And a proposition is that the number of edges is A times B, and the total number of edges is n choose 2. So we need at least this many. So this is trivial. And we were able to prove with Peter Frank that this is asymptotically correct. We used here the Rödel-Nibble method in the construction. And another variant, so this was good when A and B are fixed and n tends to infinity. It is very different when the sizes are not constant, they might increase with n. Then this is a lower estimate where here the graph entropy of Kerner was used, and we were able to prove where when A is a constant times n, so proportional to n, both conditions are proportional to n, then we obtain from this, we obtain this, and we were able to prove that this is asymptotically good again. And there are some remaining problems when one is proportional, the other one is constant. So for instance, we were able to prove this asymptotical result also for this case, which is not covered by the previous two results. And finally, let me mention a possible generalization. I am 3 minutes late, where we consider R-partite complete graphs, and we want to cover the complete graph with these ones where the sizes of all of them are bounded above. So, and this is the end. Thank you. Dhanyavad. And in honor of Ramanujan, I am telling it in Tamil also. Oh, something is wrong. Oh, no, it's okay. So, Nandri, and in honor of the organizers, Nanni.
Is there any questions?
Before questions?
Are there any questions?
Any questions from participants? So let me thank Professor Katona for his excellent contribution to this conference and his very nice talk.
So,
For listening.
Dhanyavad to Professor Katona and Nandri to Professor Armugam. And we will, there is a question. Please.
Okay. So the question is there any motivation for choosing complete bipartite graphs for partition?
Say it again, please.
Is there any motivation for choosing complete bipartite graphs
Oh, no.
for the partition?
You mean my last open question?
Yeah.
So you know, in the application, in the motivations, you not always ask a set and its complement, but it might be that there are more results. So the answers not necessarily 0 and 1, but it could be more like you probably know this old problem of heavy coin, falsified coins, that you have to use a scale. Then there are 3 answers. When you put 3 coins on one side, 3 coins on the other side, so either they are equal, or one is heavier, or the other one is heavier. Then there are 3 answers. Or in the chemical questions, chemical motivation, the color might be different. So there might be 4 different answers. So then you ask actually a partition instead of and then you add this lie situation. So then this is why it is not the size of the R-partite graph does not cover all the vertices.
Fine. Are there any other questions?
Same question. There are no further questions. So let us thank Professor Katana for his presentation, and thank you very much.
Thank you.
Yeah. Thank you. The next plenary talk is by Sandy Clauser, which starts at 3 p.m. So we have a break for half an hour.
Okay.
Okay, see you. See you, Gyula. Okay.